Hello, chemist. Jolly again. Yeah, I sound even worse, but we'll make it through this one. All right. This one is going to be on a really short chapter. It's called chapter 6, I believe, but it's basically just a review of what we've already done for reactions. So I'm looking at, where are you, chapter 6? Right there. So we've already talked about writing the equations. So we've already talked about that. That's the curly arrow notation. I wanted to point out one thing though, sequential reactions. What that means is I could say do number 1, okay? And then to those products do number 2, and then to those products do number 3. That's all I mean by sequential, is we get really shorthandy and we put them all above the reaction arrow. All right. We've already done the curved arrow, and remember that is called a mechanism. So when we're doing all of those out, a mechanism is a description of the events that take place on a molecular level as those reactants become the product. It can either be concerted or it can be stepwise. Okay, most of ours take place stepwise so that we draw out all the intermediates and then we go on. And keep in mind they're not absolute. Okay, we've come to the idea of them with our best guess. It's our hypothesis of what happens. Sometimes we have spectra proof, sometimes we don't, but it's a great visual. Remember, concerted means it happens all at once. Stepwise means 1, 2, 3, 4, and it usually forms an intermediate. And then when we were doing the curved arrow, homolysis is when you make radicals, where heterolysis is when you make the ions. And then carbocations are positively charged. And remember, Markovnikov's rule says the most stable is the most substituted. And carbanions are negatively charged. Okay, carbons, they're very reactive. They're very strong bases. They are both highly reactive, and therefore they're intermediates. They don't just stick around. The parts of the reaction are the electrophiles, okay, the reagents that are electron seeking or those that are attacked. The nucleophiles are nucleus seeking, but they are the attackers. And so what makes the best electrophiles and what makes the best nucleophiles? You know what? I'm going to start with the nucleophiles. I'm going to jump down here. What makes the best nucleophiles? And I know it's getting old me saying this, but negatives are better than lone pairs, which are better than pi bonds, which are better than polar sigmas, which are much, much better than just sigmas. All right. Why? It's supposed to have density that will go out and react, so it has to have that density, but we also have to consider not only its identity, but we must also consider the solvent that it is in. So just generically, okay, this is solvent independent. A negatively charged nucleophile is always more reactive than its conjugate acid. So for instance, OH minus is always better than water because negatives are better than just lone pairs. So the alkoxide ion is better than its protonated form, which is an alcohol, because it's negatively charged. That does not depend on the solvent. And so in a group of nucleophiles in which the nucleophilic atom is the same, okay, that was a long way to say, look, they're all oxygen, okay, it parallels basicity. And so we know the acidity trend. Remember, the acidity trend goes like that. So the basicity trend is exactly opposite. So when it's the same atom, so in this case, it's oxygen. When it's the same atom, you can actually use the basicity or acidity trends. Right? So that's solvent independent. Oh, what happens when you actually have a solvent that could, get involved? Well, then you have to look at a few features. So solvent dependent, polar protic, remember those are the ones that can hydrogen bond with themselves. is a solvent with a hydrogen atom connected to a strongly electronegative atom, which is oxygen in most cases, but remember, the ones that can hydrogen bond with themselves. The larger nucleophiles are much better than smaller ones in this case. And the reason is, I'm going to jump to the whiteboard. Gives me more room. So I have a little mantra. Of course I do. I have a mantra for everything. In polar protic, bigger is better. Now, technically, it's because they are more polarizable. But that's just not very memorable. So let's take a look at iodine minus versus fluorine minus. Okay, now remember, we're in a polar protic, okay? So I'm just going to use water. So this is a negative, so I will surround it with water. Something to that effect. Now, if you'll notice, I could get 1, 2, 3, 4 around that. Well, around this one, because it is smaller, okay, because it is smaller, you usually can't get as many around it. Now, I drew my iodine and my fluorine about the same size, but if you will, it's the number of solvent molecules around. Okay, it's the number around it. So basically, when I'm saying in polar protic, bigger is better, this iodine is very large. So it is not as solvated. And it can mush the electrons from side to side. And I know that sounds really silly. All right. But picture this. All the electrons go over to that side. Remember, it's really large. So let's say all the electrons go over to this side for just a moment. That makes it so this can escape from the water. Now remember, if it's a nucleophile, it doesn't want to just hang out with a solvent. It wants to go find the electrophile. Okay, so it needs to get away from the solvent and go find the electrophile. And because iodine is so large, it's very polarizable, which means those electrons are unsymmetrical, or they can mush very easily from one side to another, and they can, if you will, trick the water and they can get away from it. But poor fluorine, on the other hand, okay, if I was doing true to size, poor fluorine could hardly get away from that water because it is very tightly solvated because it's so small. And it's not very large, so it's not very polarizable. So it can't mush its electrons and it cannot escape from the solvent as easily. So in polar protic, bigger's better. What do I mean? In polar protic, bigger, better nucleophile because it can escape the solvent. All right, so in polar protic, that is the key. All right, so let's take a look at these. So if you'll notice, larger nucleophiles are better than smaller nucleophiles. And so iodine is the largest. So it's better than bromine, which is better than chloride, which is better than fluorine. All of those are negative. And it's very, very good for cations and anions. Okay, so polar protic really helps stabilize carbocations and carbanions. But it is the opposite of basicity. Okay, the smaller atoms can be more tightly surrounded with a solvent, okay, more strongly solvated, and it ties them up and they can't polarize their electrons, so they can't get away. The larger atoms are not as solvated and they are more polarizable, and so they can do more, mushing, more polarizable, and then they can get away. And so here's just a generic trend. This is not on your reference sheet, but it's just a generic trend for polar products. So SH, cyanide, iodide. Okay, some of those you can't tell the size, so you can look at this list. Okay, we're into the next one. What about in polar aprotic solvents? Now, those, remember, cannot hydrogen bond with themselves. So solvents whose molecules do not have a hydrogen atom attached to a strongly electronegative, or they can't hydrogen bond with themselves. And so I'm just going to draw acetone right here. Okay. Acetonitrile, DMF, DMSO. Okay. So the key to all of those is that they do not hydrogen bond with themselves. This one's slightly positive, that one's slightly negative. So it's polar, but it doesn't have that hydrogen bonding. It solvates cations very well by aligning the positive end and the negative end to your substrate or to the thing that you're trying to react with. Ah, look at this. Solvate cations very well by aligning negative ends with the cation, but not as strongly as a hydrogen bond, and the positive center is shielded, so it does not solvate the anions very well. Okay, who says we don't have a sense of humor as organic chemists? We call those the naked nucleophiles. Back to my whiteboard. That is not my whiteboard. Okay, this time we're talking about polar aprotic. All right, so wow, that was terrible. So there's acetone. Let me see, dimethylformamide. EMF, let me see, DMSO. Well, rather than drawing them all out, if you'll notice, they're polar, but they cannot hydrogen bond with themselves. All right, this is the part that I'm looking at. So we're just going to draw acetone because I think it's the best visual. This carbocation, remember, there's hydrogens there. So not a true carbocation, but that positive charge is hidden. Okay, or we could say it's shielded. Where this one is out in the open. So what I was trying to say on the other one with a visual now is the negative is out in the open and can help positive charges. But the positive is hidden or shielded, and it can't help negatives very well. So that's kind of double-sided, weird sword. You can help with the positives, but you can't really help with the negatives. Well, if things are trying to form positives and negatives, you need both of them. Clear my board here. So for instance, let's take a look at All right. So another way to draw this is that way. So whichever way you want to draw it. Let's say, just for argument's sake, that this bromine wants to fall off of that carbon, okay, just as act as a leaving group. It would try to form a carbocation and a Br minus. The only way it will do that is it has to have help forming those charges. Okay, it's never just going to fall off by itself if there isn't something else that will help it. So I need a solvent that will help both a positive and a negative. And that can be the solvent. All right, so let's take a look at polar protic. So let's take a look at a water here. Well, a water, oh, look, it's wonderful at helping out the positive. But guess what? It's also pretty good about helping out with the negative. So, polar protic helps forming positive and negative species. Okay, so I like that. It's going to help both. But what happens if I don't use polar protic? Polar aprotic can only help the positive. So erase all my little waters. All right, so remember, this is what I'm supposed to be forming. That's what I'm supposed to be forming, but this time I'm just going to use acetone. So my negative is okay, but remember that positive is hidden. So this one's still okay. Oh, look. This one is still okay. But I'm going to draw my hydrogens in so you can see it's really hidden. The partial positive is hidden, so it can't really help. Well, nature, there's only two answers to organic chemistry. It's either sterics or electronics, and this technically is both, but do you see this is sterically hidden, sterically hindered? And so it can't help the negative. And if you can't help the negative, that carbocation can never form because the negative won't come off. So it won't happen. Okay. If you can't support or you can't help stabilize the two pieces that are the products, then the reaction's not going to happen. So polar aprotics can't form carbocations very easy because it can't help stabilize the leaving group. Okay, so Guess what? This bromine over here, let's do green. This bromine over here, it's basically naked because the solvent can't surround it, okay? So if it could form, if we somehow it could form, it needs to react because nobody is helping stabilize it. And so that's what we call a naked nucleophile, is when it's not solvated very well. So right here, the polar aprotic, it solvates cations very well by surrounding them, okay? But it can't help the negatives because the positive, the partial positive charge, is very hidden or shielded. And so it leaves things called naked nucleophiles. In that case, naked nucleophiles follow basicity, okay? So a fluoride would be better than a chloride, better than a bromide, better than an iodide. Huh. Okay. All right. Now that's the nucleophile. Let's jump up to, oh, whoops, right here. Let's jump up to the electrophiles. All right. So we talked about the nucleophiles and how some of them are solvent independent. Some of those traits, having a hard time remembering words here. So some of those traits are solvent independent, but then the other times you have to really look at what the solvent is doing. Now let's look at the electrophiles. An electrophile needs to be attacked. So it has to have a spot that a bond can take place or it can accept electrons. And so the first thing is empty orbitals. Okay. So for instance, a carbocation has an empty p orbital. And so anything with an empty p orbital or positives, okay, are very, very good electrophiles. So carbocations. Anything with a really good leaving group or a polar sigma bond that can be kicked off also wouldn't mind being attacked. So weak bases, they have to be stable after departing. So the good leaving groups are I minus, Br minus, Cl minus, F minus. Okay, something that will come off. It's polar enough to be broken, and then when it pops off, it's stable enough to float around by itself. Okay, now this is just a jolly rule, but anybody with a pKa less than 8 is generally a really good leaving group. Okay, anything that has been converted from its functional group, like protonated alcohols or protonated ethers, or something called a sulfonate group. And we'll talk about these sulfonate groups when we talk about the next chapter. But if you can convert it to a good leaving group, then it can be part of the good electrophile. And then pi bonds. Now, I don't have a wonderful little mantra for electrophiles like I do for the nucleophiles. But let me see, since we're in red, this is the electrophiles. So orbitals, nope, don't want to start with orbitals. Yeah, come on. Negatives are usually better than orbitals. But then that's kind of the same as a leaving group, okay? Kind of the same as a pi bond. And they're just, they're very close, but negatives, of course. I said negative. I'm sorry, my brain just isn't 100% here today. Positives are better than empty orbitals, which are better than something with a good leaving group, which are usually better than something with a pi bond. So that's our generic for electrophiles, where nucleophiles are negatives, lone pairs, pies, polars, and then nonpolars. Okay, I have been talking a ton and you're thinking, I have no idea what you're even saying. When is this applicable? This is just all the words for when I need to do some specific reactions. So don't turn me off. Just kind of keep an idea of what all of these terms are. And then we're going to start putting them into reactions, and I'm just going to refer back to these pages. All right. How about nucleophilic strength? Again, I just want to give you a jolly reference. Okay. Strong nucleophiles are often called strong bases because they prefer to rip off hydrogens. Okay. And remember, we use the term base when we're doing acid base chemistry. Okay, this is just me again. This is a jolly rule, a pKa of greater than 18 and negative. So that's how we're going to determine whether it is a strong nucleophile. And a strong nucleophile, remember, nucleophiles can do two things. They may rip off hydrogens or they may attack carbons. Really strong ones prefer to rip off hydrogens. All right, good nucleophiles are neutral, but with a strong electronegative atom or negative that is less than 18 pKa. Okay, well, what do they like to do? Well, they tend to attack carbons. And then last, well, what are weak ones? Well, they have some kind of stabilization, so resonance or induction, or they're just really, really weak. They could attack the carbon with a leaving group, but they could also just float around. And you're like, wow, Jolly, this isn't making any sense. All right, we're going to go through the reactions really quick, and then we'll end this lecture, and then I'll do the rest in a different one. You know what? I'm going to change my mind. Let's end this lecture right there, and then I'll do a whole lecture on just reactions and then one on energy changes. So this one will just be on, let me do a little summary here. So this one was the nucleophiles and electrophiles, and basically how to identify them and their strengths. And we will use them in the next one. All right. Until next time.